Hello students, myself Ganesh Bhaglavi working as an assistant professor in Department of Mechanical Engineering, Walchana Institute of Technology, Solapur. Today we'll see mass transfer. Learning outcome. At the end of this session, students will be able to explain mass transfer and second, evaluate mass flux using Fick's law. We are going to see these 2 points: introduction of mass transfer, Fick's law of diffusion. So what is mass transfer? Whenever there is concentration difference of two different parts or species, then there would be transfer of molecules from high concentration to low concentration. So that is nothing but transfer of mass due to concentration difference. We know the mechanism in the real life, such as cooling towers. So in the cooling towers, we would like to cool the hot fluid which is already used for pre-decided purpose. So in cooling tower we are spraying the water. So water takes the heat from other secondary fluids, gets heated. That hot water is sprayed in the cooling tower from the top side. When it falls through the perforated trays, it vaporizes because of the temperature difference and unsaturated air. So that cooling tower cools the hot water by means of releasing the latent heat in terms of vapor. Those vapors gets diffused in the surrounding air. So this is nothing but heat and mass transfer. Heat transfer in the sense cooling of water, and mass transfer in the sense of the evaporated vapor getting diffused in the surrounding air. Second example, we are keeping the wet clothes for drying purpose in the surrounding. So the wet clothes contains high water molecules, high concentration, and the surrounding air is comparatively unsaturated. So because of the evaporation of water, those molecules gets diffused in the surrounding air. This is the second example of mass transfer. In the dry, third example, in the dry condition, sometimes we are using the humidifier, home humidifier. So we are generating the vapor in the boiler, small boiler for home purpose, and that is diffused in the room. Okay, so this is the next example, that is home humidifier. So humidifier generates vapor which is added in the room. So room vapor concentration increases. This is nothing but mass transfer. For next example, fourth one, when we are mixing the water, when we are mixing the salt in the water, the salt crystals get dissolved. So the concentration in the water of the salt increases. This is the very good example of the mass transfer. Now, to study the mass transfer, we have Fick's law. Fick's law is analogous to Fourier's law of heat conduction. For conduction, Fourier has given the empirical relation Q by A is equal to K dou T by dou X. So this was the Fourier's law of heat conduction. Similarly, to study the mass transfer, Fick's law suggested the empirical law. Fick's law is valid for gas mixture. Gas mixtures. So different gases might be there, like hydrogen is mixing in the nitrogen, or we know the two-wheelers, four-wheelers, automotive vehicles are emitting the CO2, NOx, carbon monoxide in the surrounding. So this is the example of diffusion. Then liquid solution. Just now we have seen the brine solution, that is mixing of salt in the water, and there are solid solutions for casting industries. As I told, it don't have any proof. So this is a empirical law, and purely it is based on the experimental evidence. Now, what is a Fick's law? Suppose in this compartment there is gas A, here gas B, and this is the diaphragm. If I puncture this diaphragm, then gas A will start flowing to the gas B, and this high concentration, suppose at this point it is a 100% concentration of A, would be decreasing towards 0, and gas B will start moving towards A. So this is nothing but the diffusion process of different gases. So what does the Fick's law states? It states that the mass flux means kilogram of that particular gas, kg of that particular gas, to the area is proportional to the concentration difference. So if I remove the proportionality constant, like conductivity in the Fourier's law of conduction, K is used. Here we are going to use DAB. So this DAB is nothing but proportionality constant, also called as diffusion coefficient, has unit meter square per second. M A is the mass flux of a gas per unit volume, per unit time, that is kg per second, and this is the concentration of component A per unit volume. So kilogram of gas A in 1 meter cube is there. So this is the Fick's law of diffusion, which is used to study the mass transfer. Now, like convection, conduction, in the mass transfer also there are modes. So we'll see two modes. First is the conduction mass transfer. Also see here we can apply the analogy. We can apply the analogy of conduction, heat conduction to mass transfer. In the Fourier's law of heat conduction, on the left hand side there was heat flux that was denoted by Q by A. Here it is a mass flux M by A. So these two terms are analogous to each other. Minus sign, there was also minus sign. Already we discussed this point. In the Fourier's law of heat conduction, K was the proportionality constant. Here D is the proportionality constant. For the conduction, there needed the temperature difference, here requires the concentration difference. So this is the analogy between conductive heat transfer and conductive mass transfer. Second mode is the convective mass transfer. So convective mass transfer example is a cooling tower. Water is vaporizing and getting diffused in the surrounding. We can have the equation mass flux is equal to H mass convective transfer coefficient for the mass transfer. Here not, it is not for heat transfer, it is for mass transfer. In the bracket, concentration of that particular gas is denoted by 1 minus concentration of second gas. So these are the modes of mass transfer and also are analogous to the convective heat transfer. You can refer fundamentals for further study. You can refer fundamentals of heat and mass transfer by Frank in Cropera. Thank you.